hydroxide. So this is pretty easy to work out if you are very careful about your units. So at first, remember, I have a millimole here. So that's 0.3 times 10 to the minus 3 mole. I like to work in hard units. I don't like, to deal in millimoles and stuff like that if I don't have to. So I have this number of moles of sulfuric acid. And so now I need to use my stoichiometry trick to get to mils of sodium hydroxide. So remember, it took 2 mole of sodium hydroxide to neutralize 1 mole of sulfuric acid. Okay, that's easy. Now I have this molarity of sodium hydroxide that I can factor into this calculation. So that's 0.5, oops, I'm going to put it on the wrong side here, 0.5 mole of sodium hydroxide per liter. And then I just need to convert this to milliliters per liter. Okay, so at the end it's going to equal something that I can't fit on that line. Ultimately it's going to equal 1,200 mils, okay? And you might say, that's a lot. Yes, it's a lot. Probably wouldn't give you that in the laboratory. But this is just a fun calculation. Okay. Now the question is, at the end of a calculation like this, you have to ask, does that make sense? And well, remember that H2SO4 has 2 protons in it, so that's really like having 0.6. And then if you were to have a solution of sodium hydroxide that's 0.6 molar, then you would only need a liter. Okay, so you can see you need a little bit more than that, and that's 1/5 more of a liter, 1,200. So you can sort of reason that in your head. All right. So now, because, like I said, the apparatus this week is more challenging than typical weeks, I thought we'd just go over how the titration experiment looks and then what some data might look like, hopefully. Oh, by the way, there's no clicker question today because on Wednesday I really screwed up. I'm sorry. I know that's the most fun. I'm really sorry. But I know this is a controversy. This will never happen again. But I accidentally unplugged it on Wednesday and deleted the clicker participation, so I can't do it. I mean, such a pain. No, I deleted Wednesdays. I have all the clicker data. And by the way, here's a good update on clicker bspace. If you've since registered your clicker from the beginning when it wasn't showing you, and then you subsequently saw yourself getting credit, we'll figure out that of course you got credit. It's just we can't continually update bspace for all the back dates. Okay. All right. So sorry about that. Promise to have a clicker question next week. So I'm going to draw this titration apparatus, but I'm going to try to center it on my page here, somewhat. This thing's a monster. I mean, you guys are going to be surprised. You're going to be mad scientists this week with all the equipment you have at your disposal. So this here is a titrant reservoir. This is a titrant reagent reservoir. Reservoir. It's a French word that I can't probably say. Yes, and it'll have lots of nice, demarcations on it. You'll have a series, actually, of stopcocks. 2. That's right. And that's going to be fun for you to calibrate and keep them set. One of them is to set the drip rate, and the other one is to turn on and off. And this will actually go through this magic device called a drop counter, okay, which is then connected to a gadget that looks about like the size of a cell phone PDA. And that little computer will be able to count drops. So it's got drop counting function. And just what you wanted on your cell phone. And it has a pH meter. Okay? Well, that'd be cool if your cell phone could do this, but not yet. All right. Now, this drop counter, you don't want that to slip into your, and there's a nice clamp that's going to hold your reagent reservoir. And so it's quite nice. You should look at these drawings in your notebook, in your lab manual. They're a lot better than I could do, but I'm really giving it a shot here. And these are on a nice ring stand. Okay, there's some ring stand here. This is a drop counter. Now, the fun part about this lab is, I've drawn this a little bit silly here. It's technically going to drip into the drop counter. And the fun thing is to calibrate this thing and make sure that the drop counter is counting drops. Because of course you don't want to be the one counting drops. That's the way I used to do chemistry, and you can see how it turned out. You want the computer to count them, but unfortunately the computer can't count that fast. Okay, and so you have to set this thing just right. A couple drops per second. All right. So then you have your beaker that you're titrating into. This is my beaker. Well, of course you always titrate into something that's blue. No, you don't really. And then at the bottom there's some stirring device. It's not quite like this, but you'll see. There's some stir bar, and the stir bar is likely coated with Teflon, and so it's very inert. Yeah, it's an inert material. And this is your reagent beaker here, where you have your unknown. You have your unknown in there. And then you're on top of this fun device called a heating stir plate. Now, please don't turn on the heat on your experiment because you do not want to fry it. But you will have 2 knobs there, one for heat and one for stirring. This is a stir knob. Okay, don't turn on the heat. No, I'm going to put a red X there. Don't do that. And that's for another experiment. I know it's fun to turn up the heat. But when you turn on that, there's a motor in there, and the motor's going to turn a magnet. And the magnet is going to turn the magnet that's inside that Teflon stir bar. Teflon's not reactive. It would be bad to put a piece of iron in your experiment, so you coat it with Teflon. But then it's magnetic, so it'll spin and stir up your solution. Probably all know about it. I love these things when I finally learned about them in high school or college. I forget. I was excited that I didn't have to stir these with a glass stir rod all the time. All right, so that's your device. And basically, with this, there's one missing piece. What's the missing link that I have not drawn yet? Does anybody know? What's missing? How am I going to measure pH? Now, you say indicator, but you're going to use an indicator and a sophisticated proton sensor called a pH probe. Yeah, this is where you get your phi recovered, because you can break all kinds of equipment. Well, don't try to recover your phi. If it's a Corning, it's orange on the top. Oh, sorry. Don't break the pH meter, please. we don't want too many of those happening. Okay, so then you'll be able to read out your pH over here and count your number of drops over here. All right, in the computer, and there's a lot of things that get going there, but essentially what you'll be able to do is, as you drop drops in, you'll be able to watch a change in pH. You will also have an indicator dye in there. I forget the one you're using, but it's appropriately chosen. And so you'll be able to know that your drop counter is really screwing up if that dye indicator isn't clicking on at the right time in your experiment, and then you better start over, hopefully on time. All right, so that's why you need to, you put the indicator dye in there to make sure that all your electronics are working. Okay, so what are the data going to look like in an acid-base titration? And so in our experiment, we are going to titrate, I don't know what my pencil, I'm really hurting myself today. Okay, you're going to titrate HCl in your initial calibration into an unknown concentration of NaOH. Okay, so you're going to titrate a known HCl into an unknown NaOH. Okay, so it'd be great to know beforehand in theory, and that's supposed to be my job. I'm supposed to help you with the theory, what a HCl versus sodium hydroxide titration curve is going to look like. In all cases, it will look approximately like this. And on this axis now, we're going to put pH. pH is the dependent variable. pH depends on the number of drops or the volume. We don't really like to plot drops. So the drop counter is smart. It's going to convert drops when you calibrate it to mils. So volume of HCl added in mil. Okay. So because you're starting with sodium hydroxide in the beaker, then you're going to start, and let's say that that pH is pretty high. It might not be exactly 14 depending on the concentration, but it'll be pretty darn close to 14, I imagine, in this lab. And then you'll be adding, and so you do need to know something about approximately these concentrations. But at some volume, when you start to reach the equivalence point, these might be say 50 mils here, 50 mil units, 50, 150, 250, whatever. Okay. And eventually, when you strike the equivalence point, oops, back to the color of my graph, then you will go very sharply downward. Okay. And it turns out when you titrate a strong base with a strong acid, and particularly in this case of titrating, say, sodium hydroxide with HCl or sulfuric acid into sodium hydroxide, that the salt that's produced is neutral, sodium chloride. That has no pKa, But water has a pKa, believe it or not, equal to 7. Okay, so that's going to set your equivalence point here. And whatever that volume is going to read out there, this is your volume. And so right when you hit, and it'll go very sharply through one transition like that, and that will, this will be your equivalence point. pH 7. Now, it doesn't always have to be the case. If you titrated, say, ammonia to make ammonium, you would find a completely different equivalence point, okay? And that's because the resulting species has a pKa that's different than water, okay? And that species would dominate, and you would see your equivalence point in a different point on the graph. So, so this is your equivalence volume here. In this particular graph here, it looks like what I got, 50, 100, 150, 200, say about 175 mils. About 175 mils is the volume at the equivalence point. Okay, so at the end here, what we want to do is now figure out, well, what acid-base indicators would I want to use? Is everyone caught up there? It's pretty straightforward in this particular example. We'll get into some other examples where it gets hairier in a minute. So, that leads to the question, what are particular acid-base indicators used in the laboratory? Because, in certain cases, you're going to want to use certain acid-base indicators, say, in the higher pKa range, and sometimes you want to use them in the lower pKa range. And so to determine this, you need to determine the right one to use so your endpoint matches your equivalence point, or is very close to the equivalence point. So remember, this is what a variety, this is basically how acid-base indicators will work for you. If you have pH on the y-axis. Now I'm going to make these strange color graphs like this. Yes? Question? Okay. So for litmus, remember litmus is one that you've all been taught. It's blue above the pKa and then reddish, dark to dark red in the acid range. So it'll look something like this, and then as you approach the pKa, yeah, it's sort of a blend of those. It might look purple, but it's, like I said, it's kind of hard to show that. So this is litmus. You could say it's approximate pKa is around neutral. And we talked about methyl orange. Methyl orange has a pKa around 5, 4.5, but I've been cheating, just rounding that. So if you looked at its color change over this range, it would be quite different. Sort of I got in trouble for not calling it orange before, right? I was using red, so now I'm really self-conscious. And so yeah, somewhere around 5, you're going to see that color change. So you wouldn't want to use methyl orange if you're trying to sense something in the high pH range. You'd want to use that to sense something in the lower pH range, right? So I need to then introduce you to a new dye that we haven't talked about yet, but one that I used to use when I was in chemistry, phenolphthalein, which has got the same sort of. That guy has a pKa of about 9-ish, let's call it. And up here, it's something that's kind of like that color. It's fuchsia, magenta, and then it's colorless. Okay, so for people that have trouble with colors, this is kind of an unfortunate part of this course. I put the colors there. Also for black and white printer folks, yes, this is kind of a deep. This is a really nice, pretty color, and then it's colorless down here. And that guy's around pK of 9, so that gives you a good indicator to use in the high pH range. And so you can do a lot of good with mixing and matching these for your experiments. So so back to our curve, our titration curve, and what acid-base indicator you might select. And now in this case, we're going to do a strong acid, and that's always a titrant what's listed first, versus a strong base. So when we do this versus notation, this is the titrant. Titrant is in the reservoir. Okay? And so we have pH versus volume of acid added. Okay, and we'll get a curve, like I said, if I'm going to do it in this color, bam. All right, so at what dye do we like to use? Let me try this again. I like to make this it's an extremely steep transition. Yeah. So it's something like this. And so now you say, well, what dye would I want to use, okay, as an indicator? Unfortunately, I can't hold them up. You hopefully can remember these. So it turns out that you could use almost any of these indicators I've shown when you're doing a strong acid versus a strong base. But you need to then be thinking which color change or what edge of the color change would best approximate the equivalence point, which is right here, the equivalence point. And so if you put these strips up there, drawn them just sort of like so, you would see that I could use this phenolphthalein. It would work out okay. If I looked exactly when it was completely colorless, not when it just started to lose intensity, but when it became completely colorless, I'd be around pH 8.2. The equivalence point is P is 7. And remember, it's going extremely steep through the transition. So I'd be okay. Turns out that would be a correct answer on the exam, and a good laboratory technique. And likewise, methyl orange would actually be okay. So you're like, wow, I don't even, Professor Krantz, I don't have to know anything for this. It's true. No. You do have to understand that this is the easiest case. But when you want to see, the color change with methyl orange, you don't want to wait until the thing has become extremely deep orange. That's a more subtle answer. You want to see just when you see a hint of orange in that yellow. Okay? So, if you can choose either indicator, but to get as close as you can to the equivalence point, you want to think appropriately. And like when you just start to see that orange come in, you'll be say around, I don't know, pH 6 to pH 5.8. Okay? So you'll only be about a unit 0.2 off, and remember you're going steeply through. So both work out, and you could see people advocate for either dye in their experiments. So this is where I had to stop last time, but the next two cases are going to be strong acid versus weak base, and weak acid versus strong base, and that's where you really have to be thinking about which indicator to use. Okay. Have fun in the lab and see you next week.